we're going to be looking at a buffer solution, and a buffer will help resist pH changes, and that is because the solution is made from a weak acid and its conjugate base in the form of a salt, or alternatively a weak base and its conjugate acid as a salt. So the example I have here is hydrofluoric acid and lithium fluoride. So we've got the weak acid, and then fluoride is present because fluoride's the conjugate base of the acid. And as usual, equilibrium dictates this. So if we look at the dissociation of the weak acid, hydrofluoric acid, it dissociates into H plus and F minus. If we look at the way we would set up an equilibrium table, the concentration of the acid is what our initial value would be here, and then the concentration of the salt would be the initial concentration of the F minus. When the weak acid dissociates, we lose a small amount X, and we gain X as the hydrogen ion, and we gain a small amount more fluoride from the acid dissociating. So strictly speaking, what we would enter in the equilibrium constant is this concentration of the acid minus X, and H plus is X, and the salt, the fluoride, would be the original concentration of the salt plus the small amount X. But as usual, we're going to assume that this small amount is insignificant, and here it's insignificant. And if we go ahead and solve for X, it would just make the math a little bit more difficult, and we would see that there probably would be very little difference in our final answer. So our equilibrium expression would be like this. Here is where the salt concentration would go. And again, you could put the concentration plus X if you'd like. And here is where the acid concentration would go. And in this case, for the pH, we would still be solving for H plus, and we would use the Ka value for the weak acid, for the hydrogen fluoride. Many textbooks rearrange this equation, and so I'm going to show that really quick. In the case of a buffer, we do not have an X squared term here because, as we'll see in the upcoming problem, the concentration of the salt would go here. So if we take this equation, I'm going to rewrite this on a separate piece of paper here. And if we write the Ka value is equal to H plus times the concentration of the F minus all over concentration of the acid. What our book does is takes the negative log of both sides of this reaction. So if we do that, if we take the negative log of all of this and the negative log of this, we have the negative log of the Ka value equals the negative log, and then we expand this logarithmic function. So product here would turn into a sum. So this would be the log of H plus. Oops, that's where the plus goes. Plus the negative log of F minus. Minus, because this is a quotient now, minus the negative log of the acid. And so the negative log of anything automatically means P. So this is P, Ka, and then the negative log of H plus would be pH. And then if we look at this term, the minus the log of F minus, and this becomes plus the log of HF. So this we're just going to recombine into one logarithmic term, and this becomes plus the log of the acid over the salt. So this kind of gets squeezed in here. So this is the Henderson Hasselbalch equation, and this would also allow us to calculate the pH just directly from the pKa. In my opinion, it is just as easy to plug values into our equilibrium expression. So if we go back to this expression, Ka is H plus, F minus all over the concentration of the acid. Then if we're solving for H plus, we're just going to rearrange the equation. So I'm going to put this over here and put the F minus down here. So this is Ka times HF divided by F minus. So either of these terms would work. Again, I typically don't tend to use equations that I have to memorize. I prefer to solve just with the algebra set up. But in either way, we'll still get the same answer. So we're going to do an example of a buffer made of hydrofluoric acid and lithium fluoride on this next sheet here. And intentionally, I have made these concentrations different. So if we have a 0.11 molar hydrofluoric acid concentration and a 0.15 molar lithium fluoride concentration, our initial conditions at as we're attaining the equilibrium expression, this would be 0.11, and we don't have any HF, assuming this hasn't dissociated, and then we have 0.15 here. The change, we're going to lose a little bit of intact HF, we're going to gain a little bit of H plus, and we're going to gain a little bit of F minus. And again, this is all in a one-to-one relationship. One of these makes one of those and one of those. So we initially had F minus in the form of the salt. So lithium fluoride, you will need to recognize that as a salt and realize that this dissolves completely, so that the fluoride present is there from the salt. So at equilibrium, this is 0.11 minus X, which is still approximately equal to 0.11 because that change is very small. And then here we have X, and for the fluoride we have 0.15 plus a small amount of fluoride from the dissociation of the acid. And again, this amount is still approximately equal to 0.15 molar. So when I set up the equilibrium expression, Ka for hydrofluoric acid is 6.8 times 10 to the minus 4. So that goes here. This is equal to H plus times the F minus, which is 0.15, divided by the HF solution. So all I've done is substitute the values in for this equation here. So as usual, the equilibrium expression for the dissociation of the weak acid governs what we're doing. We just plug those in and solve for H plus. So H plus equals 6.8 times 10 to the minus 4 times 0.11 divided by 0.15. Again, to eliminate this fraction, we're going to multiply both sides by this reciprocal. So we'll do the same thing over here, which you're going to need room to do that. Just the algebra. Okay. So that's where this comes from. Enter that in the calculator. So 6.8 times 10 to the minus 4 times 0.11 divided by 0.15. So our H plus is 5 times 10 to the minus 4th. So our concentration of hydrogen ion, 5 times 10 to the minus 4 molar. And I'm going to leave that in there and take the negative, negative log of my second answer. So the pH here, it's negative log of this number, rounded, times 10 to the minus 4, so that is 3.38. O. Okay. The next example, I would use a weak base and its conjugate acid in the form of a salt. And the way the buffer works is that the acid present will neutralize the solution if any base is added, and then this conjugate base that's already there will counteract any additional acid that is added to the system.